Hey, we're back. We are moving into the exciting part of our chapter. So far, up to this point, we have looked at systems that are determinate. We can determine the internal forces, we can determine the reactions using equilibrium alone. But, we know that's not truly how everything is built. And so we're going to take that next step in, well, how do we look at a system that is indeterminate? If I don't have enough equilibrium, what is something that I can do to get more equations so that I can find a solution? So if we look at this very first picture here, you might be lulled into thinking, oh, I could find those forces easy peasy. So we have a pin at A, which has AX and AY, and we have a force in bar 1 and a force in bar 2. So I have three things in the Y direction. The pin, a lot of times students forget that that pin is there. For some reason, we move into strengths and we start looking at these axial loads and we forget, okay? So I have AY, BY, and CY. I have an x component, AX, but there's no forces in the x direction. So the x equation is not helpful. So I have three, AY, BY, and CY. So I can sum forces in the y direction, okay? That leaves me two more, unknowns. I can sum the moments about a point. I could sum them about A or B or C, but I'm still going to have those two unknowns. So I'm indeterminate. Okay, I'm indeterminate to 1 degree. And I'm going to figure out, wow, I can use deformations because I know what's going to happen when I pull down at D. That rigid bar is going to want to rotate. So we can actually use the deformations and the compatibility of deformations as our extra equation. It's actually really, really cool. So if we're coming through our system here, we're going to walk through it several times, and you're going to understand why up to this point I have been very clear in you need to have a free body diagram for statics, for equilibrium, and a free body diagram for deformations, because you're kind of getting to that point, you're going to have two pictures, okay? So statically indeterminate. We cannot determine the reactions, the forces in our members using statics alone. So if I draw a free body diagram, I'm going to have force in AD, force in BE, force in CF. I can call them force 1, force 2, and force 3 because, because bar CF may not be the same cross-sectional area. They may look the same, but they may not actually have that same cross-sectional area. So when I'm summing forces, okay, I can sum forces in the y direction. I have force 1, force 2, force 3, and I sum forces in the x direction. I get nothing, and then I can just pick a point to sum moments about. So let's sum moments about A, and I have that unknown 2 and that unknown 3. And so, okay, I have three unknowns. I only have two equations. How do I get past this? And that's where the deformation free body diagram is going to be so, so important. It's indeterminate. We cannot determine it with equilibrium equations alone. So let's walk through what are our steps. This is super, 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 super important. Let's walk through our steps. Okay. First off, I have to determine, is it determinate or is it indeterminate? Because I don't want to do a bunch of extra work if I can use equilibrium by itself, okay? So the first thing I'm going to do is I have to draw a free body diagram to set up my equilibrium equations. And so when I draw my free body diagram, I'm going to cut those two force members and call them forces because I know they're internal forces. And I can sum forces in the x direction, I can sum forces in the y direction, and I can sum moments about a point. So if we sum in the y direction, I have FA plus FC plus FE minus 15 kilonewtons equals 0, three unknowns. I could sum moments about A, and I'm going to have force C and force E. And you're thinking, well, I'll just sum moments about E and have A and C. Well, I'll just sum it about C and have A and E. You have this twisted up mess, okay? Twisted up mess. So I have this indeterminacy, this 1 degree indeterminacy. So I'm going to look at my deformation. So what happens is I pull that bar. It's a rigid bar. It's going to want to come lower down, chances are, over here where we have the higher load. So we're going to pull down and we're going to rotate, and I'm going to draw that deformation. And I can see it has this nice little triangle and a nice little rectangle. And so I have drawn out my free body diagram for deformations, and now I can write some compatibility equations. I know that delta from C to C prime, okay, well, if I take out the delta E across, I now have that I have delta C is to 0.4 as delta, well, A minus delta E is to 0.8. So I'm able to have a relationship using similar triangles. And what is delta? Delta equals PL over AE. So when I'm looking at PL over AE, really that's the force internal. So if I'm looking at link AB, okay, and I don't know the force in it, I can relate the deformation that comes from that force A. So I have force A, length A divided by area AEA. I'm going to have the delta at C. So I'm going to have force C, length of DC divided by area of DC, E of DC, and I can relate those now back into my deformation, and my unknowns are the forces that I have in my system. So I'm going to use equilibrium equations, and I'm going to use deformation to get that extra equation I need in order to find a solution. It's actually pretty cool, and then you solve the equations, okay? So it's like, wow, we're like one step closer to learning some more advanced things. Okay, so let's just look at some different examples of where we might see, and let's think about, right now we're going to think about the compatibility. Okay, the compatibility. So if I have a column and it is made of two materials, material 1 outside of material 2. So maybe think about it as a timber column with steel plates. Okay, when I load that, the deformation is going to be the same. It's a system. So when I look at this 360 kilonewtons pushing down, I'm going to have the force of the timber pushing up and the force of the steel pushing up. I have two unknowns. I don't know how that 360 kilonewtons is divided. I don't know how it divides between the wood and the steel. Okay, so I can sum, it's all axial, so summing forces X is not helpful, summing moments about a point is not helpful. All I have is summing forces in the Y direction. So I have minus 360 kilonewtons plus the force in the wood plus the force in the steel equals 0. I have two unknowns. But what do I know about the deformation of the steel and the deformation of that timber? If I'm pushing down, their deltas have to equal. The delta of the timber has to equal the delta of the steel. And what is delta? It's the force, length, area, modulus of elasticity, and the force. So now I have equilibrium where force of timber, force of steel equals 360 kilonewtons, and I have force of timber times L over AE equals force of steel times L over AE. Two equations, two unknowns, because I'm looking at the deformations. You might also have a core, okay? You could have a core with some sort of tube around it, or a tube with some sort of core. Or you can think about concrete. Concrete and steel are two materials. They have different relationships. If I have a concrete and steel column, or I have some sort of a core with a shell, and I'm pushing on it, okay, if I'm pushing down with, again, 360 kilonewtons, how much force is in the concrete pushing up and how much is in the steel? We don't know. How much is in the brass shell? How much is in the ceramic core? We don't know. So we have this force pushing down and we have two unknowns pushing up. If I sum forces in the Y direction, I have those two unknowns. But what do I know about the deformation? If they are bonded together, if they are acting as a unit, then their deformation has to be the same. As I load the column, everything in that column is smushing down the same. So I know that the delta of the brass shell has to equal the delta of the ceramic core. I know the delta of concrete has to equal the delta of the steel. And so this is our first relationship, and I don't want you all to try to memorize these things, because there's so many different possibilities we could end up having. So we're going to go through these and we're going to talk about them, but on your own, you're going to have to just look at it and figure out the relationship. Okay, we're not going to have these pictures on an exam. They're not going to be on your homework. You're going to have to kind of do it yourself, okay? So let's look at this one. It's kind of similar, but it's a little bit different. So this time, I have this force is pushing down on B, okay? It's pushing down on B, which is got that material 2 underneath it. And there's a gap. So I'm going to be pushing down on B and then pushing and filling up that gap before I even hit the shell of material 1. Okay, so this one becomes trickier. This one you have to say, is load P enough to close the gap? Okay, what if load P is on there and we only push down that plunger 1 millimeter? Is it indeterminate? Or is all of that inner core taking that load P? Okay, so this is where you have to think is first I need to check, is the gap even closed? I'm going to see what the delta is, assuming that core takes all of the force. And if it's smaller than 2 millimeters, I know it hasn't closed. It's not indeterminate. If it's greater than 2 millimeters, then I have to rethink my situation. So I'm going to be pushing it down, and it's going to be taking part of that stress until we hit the outside shell, and then both of them are going to be working in tandem. So this time when I look at it, I know that by the time it hits the outside shell, they will both be having the same deformation. But that inner core has to move 2 millimeters. We're going to push it down 2 millimeters before we act in tandem. So this time I know that the delta of core or material 2 plus 2 millimeters equals the delta of, step back, the outside, the shell, okay, the delta of the shell plus 2 millimeters equals the deformation of the plunger, okay, because we get free 2 millimeters before it starts acting as a unit. Okay, we're already loading that inside material before we start acting as a unit of a composite system. And so we're pushing down that material to 2 millimeters before we start the composite. So this time, delta 1 plus 2 millimeters equals the change in difference of material 2. Okay, does that make sense? So first you have to check, do we even close the gap? Yes or no. If we don't close the gap, all of the force is taken by the core. If we close the gap, then we have to look at how they're working together as a system, but keeping in mind that the inside has already moved 2 millimeters. So we're going to have to add 2 millimeters to kind of catch up. Okay. So I hope that makes sense. It is kind of confusing, but you're just going to have to figure it out yourself. Okay, now let's look at this system. This system is fixed at the top and the bottom, and there are two materials, but they are stacked. They're not together. So when I'm looking at either one of these pictures, I'm putting a force on the collar. So you cannot think, oh, all of A is taking that P and C is just coming along for the ride, because C is actually attached to the top, so it's being pulled up. So that collar is putting compression into AB. That collar is putting tension into BC. So if I tried to find my reactions and I summed forces in the Y direction, I'm going to have the reaction at A, the reaction at C, minus P. That's two unknowns. And I know the reaction at A is going to be the internal force for AB, and I know the reaction at C is going to be that internal force for BC. So, and I can't do moments, it's axial, I can't do X. So I've got these two unknown forces. What do I know about the change in length of AB and the change in length of BC? As one is in compression, one is in tension. So what do I know about their deltas? I know that the delta of 1, okay, if it's in compression, it's going to be negative, and the delta of 2 have to equal 0, because our total length is not changing at all, right? Our total length is not changing. So delta 1 plus delta 2 equals 0. And delta 1, in this case, is in compression, and delta 2 is in tension. So I'm going to have a negative delta plus a positive delta. They should equal 0. And we had a homework problem, if you'll think back. We had a homework problem, I believe it was a homework problem, or maybe we did the example in class where we had 0 deformation on the top, and we want to know how much force P could be to get 0 deformation. So it was kind of like walking you into this, where the overall deformation was 0 before we got here, okay? So this time, it's the same scenario. I am applying a force at the collar, and maybe materials 1 and 2, I'm heating them up. Maybe I'm heating them up, okay? Because if I heat them up, they're gonna both increase until I kind of like touch, and then I'm going to be pushing. So when I heat it up, I may not see that there's a force in those members, but if I heat them up and they close that gap, all of a sudden they're pushing against each other. okay? So it's the same type of a system. On the picture on the right with that 0.01 inch gap, the first thing I have to discern is, am I pulling enough down? Am I pushing enough down on that collar that I'm actually closing the gap? So if POP, okay, if P, which is on system CB, that column CB, is not enough to close the gap, then it's not a composite system. We haven't closed the gap. So all of the force of P is being taken up in member BC. So what if P is only large enough to make us move 0.02 inches? 0.02 is smaller than 0.08. We didn't close the gap. All of that force is in member BC. All of the stress is carried by BC. So I have to at least push it enough to close the gap. So again, I have to check, do I close the gap or not? If I close the gap, then we start having that composite behavior. And now I have to figure out how that force is being shared between CB and BA, because they're different materials. They have different diameters. They're going to behave differently. Okay, we can't just say that they're carrying the same amount. So in this time, because I have a gap in there, then I can say delta 1 plus delta 2 equals the gap. Okay, it equals the gap. I'm going to be moving delta 2. It's going to be moving elongating. Okay, and then at some point we're going to be hitting BA and something's going to happen in there. Okay, and same with the heating. If I heat up the picture that's flat, if I heat up at some point, they're going to be pushing on each other. So the change in 1 plus the change in 2 equals the gap. And that's going to be the force in 1, length of 1, A of 1, E of 1 plus force of 2, A of 2, blah, blah, blah. Okay. What about if we have something that looks like this? Okay. If we have a link, or if we have some sort of a rigid bar with cables, or with rods in there. Okay, let's think about this again. If I sum forces in the y direction, I'm going to have AY, BY, CY. If I sum forces X, doesn't help me. If I sum moments about A, I have BY, CY. So I can see that little figure on the right, it's indeterminate. Okay, what happens when I draw? What happens when I draw the deformation? Rigid bar, rotation. Rigid bar, rotation. I now have similar triangles. The link is the same way, and you all already had a homework where you had to look at a link. It didn't have two bars, 1 and 2. It just had bar 1. So when there's just one bar there, then you can determine the force that's in that bar A, because we can sum forces to the X, we can sum forces to the Y, we can get our X and Y at the pin, and our X at rod A, okay, at rod 1. You've already had a homework like that. It was determinate. Now when we put that extra rod on there, number 2, okay, number 2, it's not so easy. If I sum forces in the X direction, I have 3. I have 3. If I sum forces in the y direction, that's great. I can get the y component of my pin at C. But I have 3 unknown x's, okay? If I sum the moments about C, I still have unknown 2 and unknown 1. So we're back to it's 1 degree indeterminate. Rigid body rotation. Take your hand, put your hand in the shape of the rigid bar and rotate it. Rotate it, and I have a triangle, and I have a triangle, and I can still have that length away and use my deltas when I'm looking at the rigid body rotation. So this is just the delta 1 over A equals delta 2 over B. That is just the similar triangles. So if we look at delta 1 in this picture right here on the right, then A is going to be 54 inches. If we look at delta 2, B is going to be 54 plus 54, because we have to go all the way down, okay? Here, if I'm looking at the rotation of how far down does D go, then I could have delta D is to 1,000 millimeters as delta B is to 425 millimeters. Or if I'm just comparing these on the left, because I'm trying to find my reactions, it's going to rotate like rigid body rotation. It's going to come over. So I'm going to have delta of 2 is to 425 millimeters as delta 1 is to 425 plus 425. Okay, it goes all the way up because that's my triangle. Okay, we could have a link that looks like this. As I pull down, I can see that link at C is going to stretch and get longer. Link at A is now in compression. it's in compression, and I still have the forces at the pin. Okay, I still have the forces at the pin. Here's a classic. This has been on the exams before. We'll have homeworks over this. I have tension and compression. So as I'm pulling down, we have rigid body rotation. Tension, our delta is bigger. Compression, our delta is getting shorter. But it's still going to be a nice, okay, similar triangle development. And here, why do we have a negative and a positive? Because one is in tension getting longer, one is compression getting shorter. Okay, so again, don't try to memorize all of these things, just try to figure out how things are related. So let's go back and look at this core and sleeve. Okay, so if I have 9 kips pushing down, and I have steel and brass, or what, aluminum and brass, whatever they are both pushing up. So I have 9 kips down, brass, steel, brass and aluminum going up. That's 2 unknowns. Okay, so there's my forces for my brass and my aluminum, and I can sum forces in the y direction because it's axial. I can't take a moment. I don't have any x forces. So, okay, I have 2 unknowns, 1 equation. What do I know about the deformation? What do I know? What kind of deformation is this going to be? Okay, if it's composite behavior, the delta of the brass has to equal the delta of the aluminum. And what is delta? Delta is force length over AE. So I have the force in the brass, the length of the brass, the area of the brass, the E of the brass equals the force in the aluminum, the length of the aluminum, the area of the aluminum, and the E of the aluminum. So I can use this system of equations to calculate the resisting force in both the brass and the aluminum, and it takes their material properties and their geometry into account. Okay, material properties, the E, and the geometry into account as I'm doing this. Okay, so then I can go back, I'm going to get that internal force for the aluminum and the brass, and I can say, okay, well, what's the stress that's acting on both of them? Because I know their cross-sectional area, I have to make sure it hasn't yielded, right? I have to make sure it hasn't yielded. What if it yields and we have a compound system like this? I will show you, but not today. Okay, I will show you. It's super, super cool. Anyway, so here's our stress. Here's our wait a minute, why aren't the stresses the same? Why aren't the stresses the same? Well, their forces aren't the same. What if their forces were the same? Would we expect the same stress? Probably not. Okay, probably not. They are going to have a different amount of stress. They're going to have a different, unless you design them where they have the same, okay, where they have the same. But why aren't the stresses the same? Okay, what do I know? I know their deformation is the same. It's composite. They are both being smushed 1 inch. Okay, they have an original link. They both have the same strain, right? They both have the same strain. So if they have the same strain, but they have a different modulus of elasticity, okay, I can have material 1, okay, at this strain, it has a stress. And I can have material 2, which might be the brass. And at that same strain, it's carrying a different amount of stress. So when I'm looking at this, because of the composite behavior, because they are acting together in their deformation, and I know their deformation is the same, that's the compatibility portion of it being a composite material, same strain, different stresses. So there's lots that we can do with this because we can now go back and figure out, well, what load could we carry? Which one's going to yield first? What is going on? This is super, super cool, guys. It really, really is super cool. We're like taking it to the next step. So I want you to really think about, really think about everything we just covered, okay? Because I don't want you to make the mistakes that I see a lot of students make. And that is just making all the materials have the same amount of force, not recognizing that they have the same strain, not recognizing what is a composite system. What does composite mean? What if I told you they aren't composite? Different behavior, okay? So anyways, this is exciting. We'll get to some examples soon. Oh, I forgot 1 stress, 1 strain, 2 stresses.